All right, and this is part two of the problem number 7 in the review packet. So the last thing we're going to check is we're going to check interval of convergence for B. So what we're going to do actually back a little bit further is we're actually going to take a look at what f of x was. And so f of x is actually going to be equal to the summation as goes to 0, n is equal to 0 and goes to infinity of -1 to the n power, 2 to the n, and then x minus 3 to the n power over n plus 1. Now, if we have this understanding that this is going to be equal to g prime of x, right, if I'm trying to figure out what g of x is, actually what I can do here is actually I can take the summation and take the derivative of this, or take the integral of this. The only thing we need to kind of keep in mind is that n is acting as a constant, even though it's technically going to infinity. We don't need to adjust it. Or if you're good at kind of being able to figure out, most likely probably from here, some type of general term to go along with it. Um, it's completely up to you, but this method also works as well. So we have to kind of isolate the terms of x, what that's going to be, and so that's this section right here. So if I were to say, what is the integral of the sigma notation, n is equal to 0, goes to infinity, of -1 to the n, 2 to the n, and then x minus 3 to the n over n plus 1. And then remember, we're doing it with respect to x. So yet again, the n values don't really matter too much. So meaning that you can actually just ignore this whole section right here. Okay, because it's all going to be some type of constant that's going to get in the way. So if I were to do the integral of this, I would actually do x minus 3 to the n plus 1 over n plus 1. Right? I would just increase the power by 1 and then place it over in the denominator. And then what I'm going to do is actually I'm going to rewrite everything else. So it's going to be another n plus 1. So this n plus 1 matches up with that n plus 1. And then I'm going to write this as the -1 to the n power and then 2 to the n. And what you'll see here is that this will actually match up fairly well with the exception of one thing. So the only exception thing is that 5. Because if I end up placing in 1, or excuse me, 0 here, what I'm actually going to get is I'm going to actually get out, I shouldn't say equals, I'm going to actually end up getting out an x minus 3 over, in a sense, 1 on the bottom, or just that x minus 3. So weirdly enough, that this is my first term of the integral section, but I forgot about one little piece here. And that little piece here is this idea that we have our plus c out in front, right? Technically, we get our plus c when we do the integration, right? This piece right here, but really what I'm doing here is I'm using this as my starting location. So this 5 is actually going to be the value that is going to be out in front. So it's going to be 5 plus the sigma notation of all that stuff. So what is technically the first term? Your first term is going to be that 5 and then fill in from that sigma notation. Now, why is this useful? Why do we need to know this? Well, what's going to end up happening is I still need to try to figure out what is the interval of convergence for this specific sigma notation, because the 5 really is not going to affect it at all, right? What it's going to do is it's just going to change the value of whatever the value that it converges to, but it doesn't change whether it converges or diverges. So we're still only focusing on this specific section. Okay, now with that done, I'm going to clean this up a bit. So sigma notation, n is equal to 0, goes to infinity, of -1 to the n, 2 to the n, parentheses x minus 3 to the n plus 1, over n plus 1 to the second power. Now that we have our sigma power series dealing with g of x, right? So I could say this is going to be equal to g of x, and then plus 5 in a sense, right? Where does this converge? Well, since this is the integral of f of x, the integral of that had, or the original had, 5 halves is less than x, which is less than 7 halves. But what ends up happening here is I need to check to make sure that the endpoints are actually part of this integral as well. So if I check x is equal to 7/2, this is going to look actually, yet again, sort of familiar. So sigma notation, -1, 2 to the n, parentheses, 7/2 minus 3 to the n plus 1, over n plus 1 to the second power. Now, this is going to yield a 1/2 to the n plus 1, which is actually just going to leave us with a 1/2 and some other things. So I will kind of set this up. So I'm going to write this as sigma -1 to the n times 2 to the n times 1/2 to the n times 1/2, right? Technically that would be to the first over n plus 1 to the second power. Now we can see that this and this are going to cancel, right? This is just our constant out in front. We can also write that as 0.5, or we could place the 2 down in denominator. And so what I have here is I have this alternating series, and I also have this n as, in a sense, the second power if I FOIL that all out. So this can be related to the p series of n to the second. And so for a comparison test, actually I can say that this value right here is going to be, well, I could also say alternating series as well, right? It's going to 0, it's decreasing magnitude, and it's alternating. So actually, that still converges. So there's many different types of things. So I'm going to say by alternating series. And then the last one to test, x is equal to 5/2 sigma -1 to the n, 2 to the n, parentheses, 5/2 minus 3 to the n plus 1 over n plus 1 to the second power. And most of you will probably figure out, right, that this is going to cancel with some of the values in here, because this is going to end up giving you -1/2 to the n times -1/2. So what's going to end up happening here is that this is going to cancel with the -1 to the n power and then 2 to the n. So that's also going to cancel out. So what I'm left with ultimately is going to be the sigma notation of -1/2 up top over n plus 1 to the second power. So the series is not going to converge because the value is actually negative itself. I could actually also put the -1/2 out in front. In fact, actually, that's what I'm going to do. So -1/2 out in front, sigma 1 over n plus 1 to the second power. And this is now not an alternating series, but since this actually kind of relates to what I was trying to talk about before with the previous one, that this could be related to 1 over n squared, which means that I can relate it back to a p series. So saying if the p series, the exponent itself is going to be greater than 1, then the series converges, and we can actually relate that because then this value is actually going to be smaller than 1 over n squared because the values in the denominator are getting larger as n increases. So we can do comparison tests, limit comparison tests, we could do ratio tests. There's many different types of ways about actually approaching this, but the ultimate thing is that this converges by, and what I'll say, comparison test. Okay, so that means that x is equal to 5/2, x is equal to 7/2, and therefore that means that I'm going to be including both of those.